Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is module 26 in my computer networks lecture series where we talk about the application layer. So, like we've been doing all the way along in this series, when we sort of progress to the next big section, we kind of step back for a second and use the OSI protocol stack to just sort of take stock of where we are. And at this point, we're almost done our discussion of the whole protocol stack because we are now at the application layer, at the very top of the protocol stack. And so just to recap where we've been, we've talked about the physical layer where the hardware exists to take binary ones and zeros, convert them into analog waveforms that can travel back and forth across whatever analog communication channel we happen to be using. We've talked about the data link layer, where we implement retransmission functionality in order to recover from errors that can occur at the physical layer, as well as implementing medium access control or MAC algorithms that help us manage a shared channel where multiple nodes are competing for that shared channel at the same time. We've talked about the routing layer. And the routing layer is where the addressing and the intelligence exists to route packets across a network that has a mesh topology where to transmit a packet between a source and a destination, we perhaps have to progress through many intermediate nodes called router nodes. And the routing layer, and IP is the most, prominent or famous example of a routing layer. The routing layer is where we implement the addressing, a hierarchical addressing scheme, as well as distributed routing algorithms that allow these routers to be able to read the address on every packet they receive and to send that packet along the next hop necessary to deliver it to its ultimate destination. After that, we talked together jointly about the session layer and the transport layer. And that we lump those two layers together because those are the layers that are combined by the TCP protocol. And the session layer is sort of the handshaking and control information necessary to establish a connection between two computers on the internet. The transport layer implements a second layer of packet retransmission to recover from packets that may be lost, not due to noise at the link level, but perhaps buffer overflow when a router is perhaps receiving too many packets and can't store them in its buffer. And so we've essentially, from bottom to top, covered how the internet works. And so now we've done this amazing thing, and now we're ready to use it at the application layer. And in a way, the application layer is it's interesting for many ways or many different reasons. So for kind of a historical perspective, which I guess I can provide some insight on because I've been around for that long, I suppose. When I was a graduate student, just graduating from university, it was during the late 90s. During what is known as the dot-com boom. And at that time, internet technology was very new, and there was a whole bunch of hype around internet companies. And those companies were basically the companies that were building the internet. They were getting all the attention. So a Canadian company called Nortel is an example. Cisco, Ericsson, Nokia, Huawei wasn't around then, but Huawei would fit into this class of companies that basically are manufacturing the networking equipment that makes the internet work. And those are the companies that were getting all the attention in the 90s. But there was a lot of hype around the internet, but the dot-com boom ultimately went bust because the applications to use the internet were not yet mature. Back then we had web, we had email, and some networked video games, not very many, and that was kind of it. And so we were building a bunch of network capacity, and we didn't really know what that network capacity was for. Now, fast forward to current times, the high-tech companies that people are excited about are companies like Amazon, Google, Facebook, Apple to a certain extent. And these are very different companies. So these companies are not the organizations that are building internet infrastructure. They are making use of the internet. And all of, for example, a company like Netflix or Facebook, they are doing all of their development at the application layer. So in many ways, the application layer is sort of the focus of the current buzz around tech companies. And so it's definitely worthwhile taking a look at it from the perspective of this course. Now, the first important thing to note about the application or the application space is that it resides in a different area on your network device. So TCP, IP are integrated into the operating system of your device. The data link layer, sometimes part of the operating system, sometimes part of the lower level driver software that exists on your operating system. The physical layer typically is embedded software or firmware inside some sort of specialty network interface or chip. But the application space application software runs within separate different programs or applications that run on top of the operating system of your device. And it's important to realize that all of the stuff that we've been talking about up until now, the IP layer, the TCP layer, session management, all that basically does is just provide the application layer with a bit pipe, right? We talked about how the purpose of TCP is essentially to make the internet kind of look like the old telephone system, where we have this abstraction that, two nodes on the internet basically have a dedicated communication channel or bit pipe to send information back and forth. But that's it. It is up to the application layer program to decide what to do with that bit pipe. And there is still a protocol, which we call the application layer protocol. There is still a protocol necessary to determine how we use that bit pipe. Who talks first, for example? What do they say? What kind of information is exchanged between the applications? This is something that needs to be defined within the application layer program itself, and it's important to note that this is very different than session management. So the purpose of session management is to establish the communication link to determine that the two nodes are able to communicate. But session management doesn't then extend to the application layer. The application layer may implement something that looks very similar to session management, but it's not the same thing. Session management exists to set up that connection on the internet. The application layer then decides how that connection should be used. And application protocols exist in basically every single program that uses the internet. Web browsers, email, network games, social media clients, peer-to-peer file sharing programs all have some kind of application layer protocol. So how do applications then make use of the internet? Well, it's basically through an application programmer's interface or API. And the most common API for internet communications is the socket API. Sockets are a very, very old concept. They were developed almost the same time as the internet and have existed to the present day. We're going to, in this module, work through an example, a socket programming example using C, which is one of the oldest languages, I guess, to use sockets, perhaps the original language. But sockets exist now in basically every programming language, every modern programming language. So you have sockets in Perl, Java, Python, C++, of course, whatever programming language you want to use. And the original architects of the socket API wanted sockets to be very, very intuitive and simple to use for programmers. And so basically they have structured them just like file descriptors. So sending and receiving data over the internet looks, from a programming perspective, exactly like reading and writing from a file. So if you want to send some information over the internet, you create a socket just like you open a file. You write to the socket just like you write to the file. That sends information to the other node that you're communicating with. If you're expecting to receive information, you read from the socket just like you read from a file. And the nice thing about TCP, remember TCP provides us this byte level abstraction. So we don't have to worry at the application layer about dividing things into packets or anything like that. We can basically just write a stream of bytes to the socket. So we can just use a character array or a pointer to a data structure, and then just write all of those bytes into the socket. And then the lower layers, TCP and below, worries about sort of chopping up all that information, putting them in packets, and delivering it to the destination. So what I'd like to do now is give you an example of a very simple application, networked application, I guess, and talk about the application layer protocol that I'm going to use to implement this networked application. And then we're going to take a look at the actual C source code, run the program. You can see a little bit about how the program works. And the source code that I'm going to be showing you in this example, I'm going to make available on my external website. The link will be in the comments below this video. And of course, if you're taking this course for credit, I'll make the source code available to you on the internal course website as well. So I'm going to be implementing a very simple message board application. And you'll recall from our discussion of TCP, or a TCP session, is that TCP takes on a client-server application. So the server creates an open socket, basically, or opens up a socket, binds an address and a port number to that socket, and then sits there and waits for connections. And then the client computer initiates connections to the server. And in most cases, when we're developing an application layer protocol, we take on this same kind of client-server model, because as you're going to see, the source code for the server is a little bit different than the source code for the client. So we need, within the server side, to create our socket first, open it up, start listening on the socket before the client can connect. And of course, a client-server model lends itself very well to a message board, because the server is going to maintain a very simple message board, and multiple clients can connect to the server, not simultaneously, only one at a time, because this is a very simple program, and read the last 6 messages that have been posted on the message board, as well as post their own message. And so I'm going to describe the application layer protocol using a state machine type diagram, similar to the TCP session management state machine that we worked through a few modules ago. And so on the server side, we start by waiting for a connection. So we sit around and we wait for a connection. When we receive a connection, we then progress to a state where we sit there and we wait for user input. And so the server in this application protocol does not talk first. As soon as it receives a connection from a client, rather than sending anything on its socket, it just sits there and it waits to hear something from the client. And again, a really important part of the application layer protocol is basically who talks first and what is the sequence for information exchange. And so we're going to basically wait for a user command packet or request to arrive from the client. And there are going to be 3 possible requests. There's going to be a request to read the information posted on the message board. There's going to be a request to post a message on the message board. And then there's also going to be a request to terminate the connection. So the client at any time can decide to disconnect from the message board. If we follow the read request flow, it's pretty simple. We're going to read the information that's stored in the message board, and we're going to send the data to the client, and then we're going to go back up and we're going to wait for the next request from the client. If we receive a message post request from the client, we're going to receive the message, update the message board with the new message, then go right back and wait for more user input. If we receive a terminate request, we're going to terminate the current connection with the client and then go back up and wait for a new connection from a different client. On the client side, the very first thing the client will do when the program starts is to create a connection to the server. And then after that, we have a wait for user input, but this block is waiting for user input from the terminal. So the client program is just going to print out a little message to the user on the terminal saying, hey, what do you want to do? Then the user presses a key to indicate what they want to do. If the user wants to read from the message board, we are going to send a read request to the server. Then we're going to print the data that we receive, and then we're going to go back and wait for the next input request from the user over the terminal. If the user requests a post to post a message to the message board, we're going to send the post message from the client inputs to the server, and then go back and wait for more user input. And finally, if the user requires or indicates that they want to terminate the connection, we terminate the connection and then we exit the program. So pretty simple message board type application. What I'm going to do now is we're going to take a look at the source code itself and step through the program, and also kind of use these state machines diagrams to sort of indicate where we are in the application layer protocol. I'm going to be sort of compressing the state machine, or sorry, these state diagrams on the next slide, so you might not be able to see them super well. So you might want to, again, sort of print out or take a screen capture of this larger state diagram so you can see kind of where we are in the diagram as we move through the code. Okay, so this is the message board server code. So at the start, we've got our GNU public license blurb. We've got a few include files. Then we've got some define statements. The maximum number of messages we can have posted on our message board is 6. The maximum length of a message is 30 characters. I've got some define statements defining the a read request has a value, integer value of 0. Post request has an integer value of 1. A terminate request has an integer value of 2. Bad programming alert. So I, for the sake of keeping the code very short and easy to read, I don't do a lot of range checking on my arguments. Most of the functions I call return values to indicate error conditions. I don't check any of that as well. This is not only sloppy programming from, possibly having your program crash, but it's also potentially a security risk for, so whenever, in particular, when you're dealing with reading information into buffers and potentially overflowing the bounds of those buffers, that opens you up for something called a buffer overflow attack, which I'm going to talk a little bit more about when we get into the computer security and hacking part of the lecture series. So anyway, all that to say, this program is for teaching purposes only and is not meant to in any way represent robust or secure internet, programming style. So having said that, we then get into the main, and then the first thing we do is we allocate some dynamic memory storage for the message board, initiate the content of the message board to the null string. That's what we're doing there. We've also got a couple of integer variables that allow the message board to kind of wrap around on itself. So we store a maximum of 6 messages, and then if we post the 7th message, it overwrites the oldest message on the message board. So we've got this kind of circular buffer thing going on. This is a temporary variable for reading in messages that we're going to receive from the clients. So that's kind of all of our memory and variable stuff. Now we get into the actual socket part of the code. This first family of statements basically does a DNS lookup. So for this example, I'm not actually running this code over the internet. I'm using something called the loopback address on my machine. So for this machine, that IP address is 127.0.0.1. And that basically allows you to run a client and server application on the same machine. So the server will bind itself to that loopback address. The client will connect itself to that loopback address, and they will be able to exchange TCP/IP packets, but those packets never ever leave your computer. So it's a nice thing to be able to do when testing client server software on the same machine. And so I just look up localhost. If I wanted to connect to a website, I could also put in, for example, www.ucalgary.ca into this string, and it would find the IP address using a DNS lookup. Once we do that, we then go on to create a socket address data structure. And this socket address data structure has a few fields in it. It has a special field indicating that this is an internet specific address. We specify the port number that the server is going to be listening on. In this case, I've arbitrarily chosen 10223 as my port number. We can basically choose anything above the 1024, the value of 1024. And then the address is basically going to contain the IP address. So this is the IP address that we got from our DNS lookup just a few statements ago. We then go on to create our actual socket. And the server, as it turns out, is actually going to use 2 different sockets. One is it's going to use for listening for incoming connections. And then when it receives an incoming connection, the socket API actually creates a second socket to communicate with the client. And the reason for that is, I don't do it in this particular program, but we could design our server to be multi-threaded. So we could have one thread within our program listening for incoming connections. When it receives an incoming connection, it spawns a thread with a separate socket to communicate to that client. Then it could go back to listen for other connections. And that way you could have a server that can communicate with multiple clients at the same time. I don't do that in this particular program, but just be aware you could. So we create our socket for listening for incoming connections. We specify that it is an internet socket. Socket stream indicates that this is going to be a TCP socket. We could use sock dgram and create a UDP socket. And then once we've created that socket, we bind the IP address and port number to that socket. So this tells the computer that this socket is associated with IP address 127.0.0.1 and port number 10223. We tell the API that we're going to be using the socket to listen to incoming connections, and we can sort of queue up pending incoming connections to give the server a chance to service them and then get back to the next one. I'm just setting the queue size equal to 1 because we're only ever going to have one client connecting to this application. But again, you could use a larger number here. And we then go into an endless loop. So I've designed this program just to be terminated by hitting Control-C in the terminal. And this is the statement where we wait for an incoming connection. So the accept command takes the listening socket as an argument, and this is a blocking, or the way that I'm calling it is, this is a blocking call. And so it's basically the accept function will not return until it receives a connection request from a client. And when it receives that connection request, it returns the socket that we're going to use to communicate with the client. So we're not using incoming socket to communicate with the client. We're going to use a second socket that I've called connection socket. And you'll notice that sockets are just integers, right? Just like file descriptors are in some Unix code. And so we've gone through all of that code and we've called the accept function, and that is basically, if we look at our state machine, where we sit in the wait for connection state. So once we start to wait for a connection, that basically means we've progressed to the point in the code where we've called the accept statement. And if we go back up to our terminal here, I can compile the message board server program and run. And we see we've got two output statements. That actually comes from up here on the code. This is where we indicate what our host name is. We specified localhost. And then this is a printout of what the IP address is that we get from our DNS lookup. And it is the loopback address 127.0.0.1. You'll note that we do not yet print out the new connection statement here. And that's because this accept function call is blocking. So this is where the program is hung up right now. It will not proceed until we get a connection from the client. And so let's then go over and take a look at the client code. So the client code, again, the GNU public license blurb, the include statements, similar define statements to the server program. We have a little menu data structure here so we can print things out to the user, the terminal user, so they know what numbers to press to do different things on the message board. Same bad programming alert. So we start out by doing a similar DNS lookup for the server IP address. But this is being done for a different reason. So the server had to look up its own IP address basically because it had to bind its socket to essentially its own IP address and its own port number so that the operating system knows where to listen for connections. The client, however, in sort of a normal application would exist on a completely different machine. And so we would then put in the name of the server here, not because we're trying to bind to something local, but because we're trying to make contact with a machine that's somewhere, across the internet. So we're using localhost here, but we could put in www.ucalgary.ca because that is the machine somewhere across the internet that we're trying to connect to. We create a IP address data structure that's identical to the server, and we create a socket using exactly the same socket call that the server used. However, this is where the connection, or this is where the code starts to look a little bit different. So in the server, we then created an incoming socket and we bound to it and we said we were going to listen on it, and then we called the accept function. The client doesn't have to do any of that. So the client has created a socket with the IP address and port number of the server that we're trying to connect to, and then it just calls the connect statement. And the connect statement then initiates a TCP connection to the server. And then at that point, we go into a loop where we basically ask so this code prints out a little menu on the terminal to the user and then gets user input. And then we go into a switch statement that will do different things depending on what the user is asking to do. So if we go over here and we compile the message board client program and we run it, we see two things have happened. One is in the client side, we get a printout of localhost and IP address. That's the server that we're trying to connect to. We then get our little sort of menu and our prompt asking the user to indicate what they want to do. But over here in the server window, we now got a little message that says, oh, we've received a new connection. And so if we go back to the server code, what's happened is our accept function has returned because we've initiated a TCP connection. It's returned our connection socket. We have printed out new connection, and then we enter a loop where the first thing we do is we call a receive command. So this is our first socket communication statement. So if we want to transmit data over a socket, we use the send command. If we want to receive data from a socket, we call the receive command. And so right away, because within our application layer protocol, within our state diagram, we said, okay, well, the client talks first. The server just waits to see what the client wants to do. And so in our code, we call the receive function because the server knows that it's going to wait for something to arrive from the client. And this receive function is basically just going to block. So it's just going to sit there and wait until it receives information from the client. And we can specify how much information we want to receive. So the requests that we receive from the client we're representing by integer values. And that's what these define statements are for. So an integer value of 0 is a read request. An integer value of 1 is a post request. And an integer value of 2 is terminate. And so we're going to use the receive command on the connection socket, which is the socket we're communicating with the client. We're using to communicate with the client. And we're going to ask it for an integer value. So we're going to ask to read in the number of bytes that correspond to an integer, 4 most likely. So this is probably a 32-bit machine, and or 32-bit integer. And then we give it the address of the variable that's going to store that incoming command. So this is exactly like reading from a file, right? When you read from a file, you give it a pointer and you give it how many bytes you want to read from the file. However, we're reading this from a socket. So we're actually going to just sit there until we receive this information over the internet from the client. And if we look at our server state machine, we have now progressed from waiting for a connection to waiting for user input. And the wait is implemented with this call to receive. On the client side, we've created the connection, and we have now progressed also to the wait for user input section. But when we go back to the client code, we've printed out our little menu, and then we're reading in information or a command from the user on the terminal using the fgets function call. So this function call is going to sit there and wait until the user enters something onto the terminal. And so The wait for user input on the client side is waiting for terminal input, and the wait for user input on the server side is waiting for a command to be sent by the client once it receives that terminal input. So now on both the client and the server code, we basically have a switch statement that handles the different requests that we can receive from the user. And so the first thing I want to do is just read the message board. The message board is going to be empty. So over here in my client program, I'm going to type 0. And we got a message board, bit of message board output. Nothing's there because the message board is empty. On the server side, we got a little terminal message saying it received a read request. And if we look at the code, when we pressed 0, the value 0 was stored in the integer tx request. That would cause us to skip down here. And then the very first thing that we do is we send a bit of information to the server. We're going to send the integer value of 0 to the server over the connection socket. Then we're going to print a little message board header message. And then we're going to loop for 6 times, and we are going to use the receive command to receive the 6 different messages that can be posted on the message board. And when you look at this receive command, we're passing a pointer to the string buffer, which is big enough to hold our 30-character message. And we're indicating that we want to read in max message length, which is 30, times the size of a character in bytes, which is going to be equal to 1. So we call the receive command exactly 6 times on the client side. On the server side, when the server receives a read request, it prints out the little message we saw on the terminal, and then it goes straight to reading the 6 messages posted on the message board and sending them separately as 30-character strings. And so these 6 send commands correspond to the 6 receive commands that we implement on the client side. And you could say, well, how does the client know that we're gonna, receive exactly 6 commands from the server? What if the server decides to send only 2 commands? This is all about the design of your application layer protocol. The application layer protocol in this particular example promises that the server will always send exactly 6 messages, and the client should receive those same 6 messages in a loop. And so this is just, you program it this way. You could have chosen something different. You could have, configured the server to only send non-null strings, for example. But then you would have had to build intelligence on the client to be able to handle a variable number of messages from the server. Maybe another bit of information would be sent from the server saying, okay, I'm going to send you 2 messages, or I'm going to send you 3 messages, something like that. But I did it this way just to make it simple. If we then go back to, and then if we look at our state machine, the read request makes the server go in this direction. So we read from the message board, and then we send the message data. And in the actual code, these states are implemented in basically one loop. So we simultaneously read from the message board by accessing the message board array, and then we send by calling the send command. On the client side, we send our read request. So that's implemented here with this statement. And then we receive and print the data. That's implemented in this loop. So to make things more interesting now, let's post a message. So I'm going to request to post a message. I'm going to, there's nothing in the protocol that says this, but I'm going to say, I'm going to identify myself as Kermit, and I'm going to say, hello, ? And if we look at the code for a post request on the client side, we send our post message, and that's actually broken down into two statements. The first send statement is just the post command that makes the server aware that we want to post something. And then separately, we send a second message with the actual message that we want to send after we prompt the user for that message, which is done with that fget statement. On the server side, we receive the post message. So we receive our 30-character message, whatever it is from the client. We copy that message over to the message board. I probably could have just passed a pointer to the message board here and saved us this extra call to memcopy. Then I do a little bit of updating of these index variables that allow us to have this circular buffer thing on our in our message array, and that's it. So that's the update message board option or state. Then we go back to waiting for user input in the server. So we go back all the way to this this receive command where we wait for we wait for another command packet to come from the client. And on the client side, we loop all the way back to accept user input by going to the top of the do statement, where again we wait for user input from the terminal. Just to check and make sure that everything worked, we can read the message board to see if our message was actually posted. Sure enough, it was. So we have our message from Kermit saying hello ? And let's say that this is all this user wanted to post. So we are going to then terminate the connection. So we're going to hit 2, terminate request received by the server. The client program exits. And so if we look at the client, the client state machine, pretty simple. We terminate the connection and then we exit the program. How does that look? On the client side, we send the terminate notification to the server. Then we drop out of our do statement and we close our connection socket. On the client side, we want to terminate the connection and then go back to waiting for a new connection from a different client. And so if we look at the server code, we print out we've received a termination request. We close the connection socket. And remember, this is the socket that the accept statement gave us to communicate with this specific client. And so when we close this connection socket, we're closing the connection with this particular client. We then drop out of the do statement and loop back to the start of our while one. And the next thing we do is we call the accept function again for the socket we're using to listen for incoming connections. So we've terminated our current communication session with our current client, and then we go back to listening for a new client to connect to us by recalling the accept statement. And so if we wanted to run the client program again, the server would register this as a new connection. We could read the message board. Sure enough, the message from Kermit is still there. We could post a message of our own. Hello back. Read the message board, and that message would be on the message board. And so this second connection is basically treated as an entirely new client, although the server, as you would want from any message board program, remembers what the other people have said on the message board, so you could in theory use this to communicate with multiple people. So this is again a very simple example, super simple state machine, but hopefully it gives you a notion of what it's like to program with sockets. The main thing that I want you to take away from this example is that, how messages are exchanged, how many messages are sent, who waits for who to talk next. This is completely under your control as the programmer. And as you make these decisions and implement these decisions, you are essentially implementing an application layer protocol. And finally, one last word about poor old layer 6. So you'll notice that in all of my diagrams and in all of my discussion, I've not mentioned the presentation layer, which is the 6th layer in the OSI protocol stack model. And essentially, now we're done, right? We're done talking about the protocol stack. We've gone from the physical layer all the way up to the application layer, and somehow I didn't talk about the presentation layer. And that's because the presentation layer isn't really commonly included in most modern protocols anymore. Initially, it existed to deal with the different byte orderings that occurred on different machines. Big Endian ordering versus little Endian ordering. It's not so much of an issue anymore. Most machines are pretty much standard. So the presentation layer is usually not included or discussed. You will see some people talk about conceptualizing encryption as a presentation layer protocol, but it's relatively rare, as we're going to see when we talk about when we get into talking about network security. So this is it. So we've essentially, if you've watched all of the videos up until now, and if you have, thank you for hanging around, gone from the very bottom, literally analog wires carrying analog waveforms, all the way up to a networked internet application, simple message board program that uses sockets. And I should say, even though the message board code was a very, very simple example of a networked application, it fully works. So even though I tested it on the loopback address, the localhost address, we could bind it to an internet visible public IP address, and anybody in the world could use our client program to connect to it. So it is in that sense, it is a fully fledged internet ready application, even though it's ridiculously insecure and sloppily coded.